Hello everyone. In this video, we're going to talk about the strategy for deciding whether a given series converges or diverges. Before we go through the actual strategy, let's recall all of the tests that we have in our toolbox. First, we have the divergence test, which says that the terms of a series must go to zero in order for that series to converge. The divergence test is usually very easy to apply, and so it is almost always a good first step. Next, we have the geometric and p-series tests, which we apply when, you guessed it, we're given a geometric or a p-series. Then we have telescoping series. These are fairly rare, but we can apply the telescoping series procedure to any series of the form sum of fn minus fn plus 1, where f is some function of n. After that, we have the comparison and limit comparison tests. We apply these when we're given a series that looks like a geometric or a p-series. Next, we have the alternating series test. We can use this one whenever we're given an alternating series. Then, we showed that absolute convergence implies convergence, and so we can test for absolute convergence. This is usually helpful when we're given series involving something like sine of n's, or cosine of n's, or a certain alternating series. And finally, in the last lecture, we introduced the ratio test and the root test. The ratio test is useful for series containing factorials or powers of constants, like 3 to the n. And the root test is useful when the series looks like something raised to the nth power. And there we have it. These are all of the tools that we can use to determine whether a series we come across converges or diverges. To end this video, I thought it might be good to go through a rapid-fire round of examples and identify which test we would use in each case. So, here we go. For the sum of minus 1 to the n over square root of n, we can start by using the divergence test. But that fails since the terms do go to 0. However, we notice that the series is alternating, and so we can use the alternating series test. For the sum of n over natural log of n squared, we start by using the divergence test, and we find that that works since the terms go off to infinity. For the sum of 3 to the n plus 1 over 2 times n factorial, the divergence test doesn't work, but the factorial tells us that the ratio test is probably a good idea, and it turns out that that works. For the sum of cosine of n to the n over n to the fourth plus 1, the divergence test doesn't work, but the cosine indicates that testing for absolute convergence may work. After taking absolute values, we find that we can compare the series to 1 over n to the fourth, which does the job. For the sum of 1 over 2 to the n, we realize right away that this is a geometric series, and so we're just done. Similarly, for the sum of 2 over square root of n, we see straight away that this is a p-series, and so we're also done. For the sum of 3n squared plus 2n plus 1 over 2n squared plus n, the divergence test works, since the terms go to 3 halves. For the sum of n squared over n cubed plus 1, the divergence test doesn't work, but we can use the limit comparison test with n squared over n cubed, which is equal to 1 over n. And for the sum of sine of n squared over n squared, the divergence test again doesn't work, but the sign indicates that testing for absolute convergence might work. Taking absolute values, we find that we can compare this to the sum of 1 over n squared, which turns out to work. For the sum of n to the n over n squared plus 1 to the n, the divergence test again doesn't work, but we see that we can write each of the terms as something raised to the nth power, which tells us that the root test may be a good idea, and that turns out to work. For the sum of 3n to the third plus 2n plus 1 over 2n to the fifth plus n squared, the divergence test doesn't work, but we can use the limit comparison test with the sum of n cubed over n to the fifth, which does the trick. For the sum of n over natural log of n, the divergence test actually works, since the terms go off to infinity. For the sum of 2 to the n plus 1 over 3 times n factorial, the divergence test does not work, but the factorial tells us that the ratio test should do the job. For the sum of 2n squared plus 7 over the square root of n to the 7th plus 2, the divergence test does not work, but we can use the limit comparison test with the sum of n squared over n to the 7 halves. And for the sum of 2 to the 1 over n minus 1, the divergence test again does not work. But we notice that the term on top is insignificant since it goes to 1, and therefore we can use the limit comparison test with the sum of 1 over n. For the sum of e to the n over n plus e to the n, it turns out the divergence test works since the terms go to 1. For the sum of minus 1 to the n over natural log of n, the divergence test does not work, but the series is alternating, and so we can use the alternating series test. For the sum of 2n squared over n to the fourth plus 1, the divergence test does not work, but we can use the limit comparison test with the sum of n squared over n to the fourth, or we could use the direct comparison test with the sum of 2n squared over n to the fourth. For the sum of n factorial over 3 to the n, the divergence test turns out to work, but the limit can actually be a little tricky to compute. And so we could also notice the factorial and use the ratio test. Either way works. And finally, for the sum of n squared plus 1 over n to the fifth minus n squared square root of 3, the divergence test does not work, but we can use the limit comparison test with the sum of n squared over n to the fifth. And there you have it. Hopefully, by the end of this, you're feeling a little bit more comfortable with the tools that you have at your disposal. And with a little bit more practice, I'm sure you'll be able to handle any series that we could possibly throw at you. That's all I have for you this time, and have a great rest of your day.